So today we have as a speaker Armando Capasso from the Università degli Studi di Trieste. My Italian is not good. Sorry about that. He's going to talk us about curved semistable Higgs bundles over smooth complex projective varieties whose canonical bundle is ample. Thank you very much.
Thank you for this invitation. Welcome to everybody. I share my screen. As Marina said, I shall talk about curved semistable bundle over smooth complex projective varieties whose canonical bundle is ample. This talk is divided in three parts. The part 0, where I recall the basic definitions about Higgs bundles and Higgs sheaves. The part 1, where I will introduce so-called positivity conditions for Higgs bundles, and I will explain some details. And in the second last part of this talk, I will apply this positivity condition to the study of geometry of smooth complex projective varieties whose canonical bundle is ample. So let's start. In this talk, by X I mean a smooth projective variety over an algebraically closed field K of characteristics 0 unless otherwise indicated. By X sheaf, I mean a pair E phi where E is a X coherent sheaf on X and phi is a morphism from E to E twisted by capital omega 1 of X, such that phi wedge phi is 0. This is the so-called integrability condition. And here I recall what is this morphism. Of course, capital omega 1 of X is the cotangent bundle of X. Higgs quotient sheaf of E is a quotient sheaf Q of E such that the corresponding kernel K is phi invariant. I mean, the image of K is contained in K twisted by capital omega 1 of X. And of course, Higgs bundle is a Higgs sheaf whose underlying sheaf is locally free. From now on, let it be rank R torsion Higgs sheaves on X. Here, H is a polarization of X. I recall that the slope of E with respect to H is given by the ratio between the degree of the determinant line bundle of E with respect to H over the rank of E. In general, this number is rational. Of course, this slope depends on the fixed polarization. And to be exact, I need to say H slope with respect to H, and so on. But from now on, I'll skip any reference to H. So I recall that Higgs bundle is semistable, respectively stable, in the sense of Mumford-Takemoto, if mu of E is less or equal than mu of Q, or mu of E is less than mu of Q, for every torsion Higgs quotient sheaf Q of E, where the rank of Q ranges between 1 and R minus 1. If this condition is not satisfied, then is called unstable. And about semistable sheaves, Bogomolov and Gieseker proved in the complex setting and Langer in the general setting with no reference to the characteristic of the underlying field, they proved that Higgs bundle E is semistable, then this inequality holds. For simplicity, this term I call capital delta of E, and this is the so-called discriminant class of E. In the next, I will recall this class because it's fundamental in order to state my results. So, in a work in progress, I proved a Lefschetz principal type theorem. I mean, if I change the underlying field via a field extension, one obtain, of course, another smooth projective variety of the same dimension. The canonical morphism from this new variety x of f to x is fatally flat and quasi-compact. But the result is the pullback of E via F is semistable Higgs sheaf if and only if the original Higgs sheaf is semistable. Of course, where the Higgs field phi vanishes, one recovers the Langson results. And to conclude this first part, if E is an unstable torsion-free Higgs sheaf on X, one can consider the so-called Harden-Arrasima filtration. I mean, a filtration of E in Higgs subbundle, Higgs subsheaves EM, EM1, M-1, E1, E0, such that successive Higgs quotient sheaves EI over EI-1 are semi-stable for any I. And moreover, the sequence of the slope of these quotients is strictly decreasing. One posit the maximal slope of E equal to mu1 and the minimal slope of E equal to mu m. Of course, this filtration is trivial in the case where the Higgs sheaf is semi-stable. And it's more important to note that the Harden-Arrasima filtration that exists unique for any Higgs sheaves. So, after this, I start the part 1 of this talk. So, I recall you that for any rank R vector bundle over a smooth projective variety, one can consider the Grassmann bundles. I mean, a Grassmann bundle which parameterize the rank as locally free quotient bundle of a fixed E. Over these Grassmann bundles, one can consider the so-called universal short exact sequence given by this first row. Okay, sign. Okay, for any S between 1 and R minus 1. Of course, because I'm considering Higgs bundles, I can pull back the Higgs field from E to P pullback of E. One can twist this universal short exact sequence by the cotangent bundle of the sorry. One can twist with the cotangent bundle and the Grassmann bundle and obtain another short exact sequence because the base variety is smooth, hence the Grassmann bundle is smooth, so the cotangent bundle is locally free, and hence the twisting by a locally free sheaf preserves the exactness. So one obtains this other short exact sequence. Okay, this is easy. Now, as I said, Grassmann bundles of the S rank Grassmann bundle parameterize rank S locally free quotient bundle of E. But now I need to parameterize rank S locally free quotient Higgs bundle, Higgs sheaves of E. So what is the idea? The idea is to consider this composition and to consider the closest subscheme of the Grassmann bundle where this composition vanishes. In this way, one finds a closest subscheme of the Grassmann bundle, which in general it is only projective. Indeed, there are examples where these schemes are not equidimensional, not reduced, maybe are not irreducible and not smooth. So these are projective schemes. Stop. These are called, of course, Higgs-Grassmann scheme because they satisfy the following universal property. Okay. From this blue composition, one has that the pullback of this field restricted to this Higgs-Grassmann scheme carry on the Kate universal quotient bundle of E another Higgs field, and this pair is called rank K universal Higgs quotient bundle of E. Since it satisfies the following universal property. I mean, given a Higgs bundle E, in order to construct a Higgs rank K quotient bundle of E, one needs to consider a section of the Kate Grassmann bundle of E, which takes value in the Kate Higgs Grassmann scheme, and vice versa. If I take a section of the Kate Grassmann bundle which takes value in the Kate Higgs Grassmann scheme, then one find a rank K Higgs quotient bundle of E. This justifies this definition. One needs this Higgs Grassmann scheme in order to give positivity conditions for Higgs bundles. In this case, I mean the so-called ampleness and nefness. Okay, what do I mean? Ugo Bruzzo and Beatriz Graña Otero gave the following definition. Higgs bundle E of rank 1 is said to be Higgs-ample or Higgs-nef, H-ample or H-nef for short, if E is ample or nef in the usual sense. That is, in rank 1, one does nothing. But if the rank of E is greater or equal than 2, one says that E is H-ample, H-nef, if all X bundle QK of E are H-ample, H-nef for all K, and the determinant line bundle that of E is ample or nef in the usual sense. Okay. This definition is not so clear at this moment. Indeed, in the next frame, I will explain it in the rank 2 case and the rank 3 case. For the moment, we don't confuse H of H-ample, H-nef with the polarization H of X. First. Second, if the Higgs field vanishes, then one finds again the usual definition of nef and ample vector bundles. Third, for what we know until now, the first chain class of these Higgs bundles satisfy the usual positivity conditions of the positivity condition, which I have written here. Until now, we don't know whether the sure polynomial of chain classes of Higgs-ample or Higgs-nef Higgs bundles satisfies analogous properties. Until now, these results are completely unknown. Okay, now I explain this definition in the rank 2 case. For example, what is an H-nef rank 2 Higgs bundle? First step, since the rank is 2, there exists just one Higgs Grassmann scheme, GR1 of E. By definition, one requires the nefness of the following line bundles: the determinant of E, which lives over X, and the nefness of the rank 1 universal Higgs quotient bundle of E, which lives over GR1 of E. That's it, the rank 2 case. Now I pass to rank 3 case. What is LHNF rank 3 Higgs bundle of X? First step, in this case there exists two Higgs Grassmann scheme, GR1 of E and GR2 of E. By definition, I need the H-nefness of the following Higgs bundles: the determinant bundle, the rank 1 and rank 2 Higgs quotient, universal Higgs quotient bundle of E. Okay, the determinant bundle of E and the rank 1 universal Higgs quotient bundle of E are both line bundles, and we know what is an F-line bundle. So we need to apply the previous definition recursively to the rank 2 universal Higgs quotient bundle of E, which lies over GR2 of E. So by recursion, I need to require again that the determinant of Q2 of E is nef, and the Q1 of Q2 of E is nef. Again. Okay? So at the end of the day, the Higgs nefness and the Higgs ampleness are equivalent to the nefness of the ampleness of a collection of line bundles which lives over projective schemes. This is the idea. At the beginning, this is not so easy to understood, but if one works with this definition, all becomes very, very clear. And this is the strong point, for this is the cornerstone of all the proofs for these particular Higgs bundles. Okay, this is the first part of the example. The second part I consider was given by myself, Ugo, and Bea. We considered a curve X, smooth reducible projective curve X of genus greater or equal than 2, And so the following is bundle given by the dark sum of two line bundles L1 and L2, such that phi of L1 is contained in L2 twisted by omega 1 of x, and phi L2 is equal to 0, where degree of L1 is D1 and degree of L2 is equal to D2. Okay, first the condition, D1 is less or equal than 2G minus 2 plus D2, then the Higgs field is different from 0. If the sum of the degree is positive, then the determinant line bundle of V is ample, of course. And if D1 is positive, then the rank 1 universal Higgs bundle of V is ample. Thus, under these conditions, E is Higgs ample. Okay, that's all clear. But if the genus is free, D1 is 2, and this 2 is equal to -1, then E is not ample as ordinary bundle, even if E is ample. And if G is equal to 2, D1 is equal to 1, and D2 is equal to -2, then E is not example, even if Q1 of E is ample. Okay, what's the point? The point is an ample vector bundle or an F vector bundle is X ample or X nef, respectively. But the reverse does not work. First consideration. Second consideration, the condition on the determinant line bundle is not optional. Otherwise, one can find a X ample vector bundle which degree is negative, and this is not nice in my humble opinion, from one hand. On another hand, we need of this condition because otherwise the Barton-Kleiman criterion for this ampleness does not work so nice. So what are the properties of example Higgs bundle? By myself, Ugo, and Bea, we have proved the usual properties. I mean, the finite pullbacks, quotient of Higgs bundles, tensor products, extension of H ample Higgs bundles are again H ample. And in particular, we have proved a Barton-Kleiman type criterion for Higgs ampleness. From these results, we have also proved that the extension of Higgs nef Higgs bundles are Higgs nef. The original proof of Ugo and Bea works only in the complex setting, and we obtain a Barton-Kleiman type criterion for the Higgs nefness. Okay? Sorry. Okay. What does say this Barton-Kleiman type criterion for Higgs nefness? For Higgs ampleness, sorry. It says the following. Let it be a Higgs bundle over X, and we fix an ample class H, numerical class, an ample class. Okay. E is H ample if and only if the determinant line bundle is ample, and there exists a real positive number delta H, such that for any finite morphism F from an irreducible smooth projective curve to X, the inequality minimum slope of the pullback of E over C is greater or equal than delta H times the degree of the fullback of H over C. Okay, two things. First of all, this real positive constant delta of H does not depend on F and on C. It depends only on the Higgs bundle E and on the ample class H. I mean, if one changes the ample class H in H0, one finds a delta H0. If one changes the Higgs bundles, of course, delta H changes fraction of Higgs. Second thing, in the next of this seminar, of this talk, where I say F from a morphism from F from C to X, I mean a finite morphism from a multi-reducible projective curve to X. Okay, I shall not repeat it again. This is our theorem by myself, Ugo, and Bea. The Barton-Kleiman type criterion is the following one. E is X ample if and only if the determinant line bundle is ample, of course, and there exists a real positive delta constant delta H such that for any finite morphism f from C to X and for every X quotient bundle Q of f pullback of V, the inequality degree of Q is greater, the degree of Q is greater or equal delta H times the degree of f pullback of H over C. Okay, this is very similar to the usual Barton-Clement criterion for the ampleness of vector bundles. The big difference is in the first line. Here we need to require the ampleness of the determinant line bundle. Otherwise, we can find, I repeat, X ample X bundles which are not ample in the usual sense, and this is not good for us. Okay, now I'm explaining example due to Mumford. Okay, the history is a little bit, the history is not linear. Archon, by a suggestion of Seshadri, proved the following theorem. Let X be a complexly reducible smooth projective curve of genus greater or equal than 2. There exists a rank 2 degree 0 stable vector bundle E over X such that the symmetric powers of E are semistable. Okay. In general, this theorem works in any rank, but I need only the rank 2 case. Previously, Mumford, in 1966 circa, he said, okay, I take a curve X and a stable vector bundle E such that blah, 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 and I construct the following example. But the problem between quotes is that at that time, Mumford does not know whether a such vector bundle exists. Indeed, we need to wait for this result of Archon and Seshadri. So, what's this Mumford example says? Okay, I consider the projective bundle of E, which I call Y, the canonical projector pi from Y to X. I consider the divisor correspond to the tautological bundle of E, and by C I mean an irreducible curve in Y. Okay, if C is contained in a fiber of pi, then the degree of D over C is equal to 1. Otherwise, let M be the degree of C over X. C corresponds to a rank 1 subbundle M of mth symmetric power of E. Since E is satisfies this condition, the previous condition, the degree of M is negative. Hence, the degree of D restricted to C is equal to M degree of E minus degree of M. But the degree of E is 0, the degree of M is negative, so this degree is positive. By all this, D is an F divisor which has positive degree over every curve. But the auto-intersection of D is 0, so by Nakai-Mosheson criterion, this D is not ample. That is, the vector bundle E is an F, but not ample. Okay? Now, I use this example. I consider an ample line bundle A over Y. I consider the following rank 2 vector bundle, A twisted by a big N, that sum with the tautological bundle of E. This is a rank 2 vector bundle of Y such that the determinant line bundle is ample. The pullback of F to any smooth reducible projective curve is positive, but F is not ample because it has a non-ample quotient. So this example proves that our Barton-Clement type criterion works if we consider the ampleness of the determinant line bundle. Otherwise, I repeat, we can find X bundle which are X ample, and the underlying vector bundle is not ample, and this is not good for our aims. Okay? Okay. Now I give a sketch of the proof of the Barton-Clement criterion. Let us assume that the determinant line bundle is ample. As I said, the Higgs ampleness of E is equivalent to the ampleness of a collection of line bundle L of S, where S is this the generical Higgs-Grassmann scheme iterated a lot of time. Okay. Using the properties of the Harden-Arrhenius filtration of the f-back of E, where f is the composition from C to S to X, we prove the ampleness of the all LS line bundles. In est, we have the H ampleness of E. On the other hand, if E is H ample, first of all, the first check class of E is ample. Thus, for any f from C to C bar over X, there exists a real positive number epsilon such that the degree of the first chain class of f back to C is greater or equal to epsilon degree times the degree of f back of H, where H is a fixed ample class over X. So we need to distinguish two cases. First, if f back of E is semi-stable, then the slope of f back of E is, of course, greater or equal to the epsilon over the rank of E times the degree of f back of H. Otherwise, one consider a morphism from C to X Grassmann scheme of E such that the pullback of the rank S universal Higgs push bundle of E is exactly E of M over EM minus 1, where S is the rank of this Higgs bundle. From all this, the minimal slope of f back of E is the following number. Since QS of E is H ample by hypothesis, there exists eta, a real positive number, such that the first chain class of QS of E minus eta rho S pullback of H, where rho is the canonical projection of the Higgs Grassmann scheme over X, is again an ample class for all possible value of S. So we have this inequality by the usual Barton-Kleinman criterion. From all this, one fix delta of H equal to the minimal between epsilon over rank of E and eta over rank R minus 1, and one has the claim. That's it. Now, in order to conclude this first part, I recall this important definition, which is the cornerstone of the last part. This last part, I introduce a very important class of Higgs bundles, which are the curved semistable Higgs bundle. What do I mean? Let E be a rank R Higgs bundle over X with R greater or equal than 2. By a curved semistable Higgs bundle, I mean Higgs bundle such that for any morphism f from C to X, the pullback Higgs bundle f star of E is semi-stable. Respectively, curved stable means stable. Okay. Why are these bundles very important? From these theorems. If E is semi-stable and the discriminant class vanishes, then E is curved semi-stable. But if E is curved semi-stable, then is semi-stable. We don't know whether the curved semistability of E implies the vanishing of the discriminant class. This is, for me, is the $1 billion questions. But this is another history, and I will not enter in details. Okay, this is one important thing. Another important items is that the curved semistable Higgs bundles are semistable with respect to any polarization of X. So in this case, the polarization is usualless. In the case, I repeat, in the case of curved semistable Higgs bundles, the polarization in some sense is usualless. Of course, in order to compute the slope, the degree, and whatever you want, I need of a polarization. But the curved semistability does not depend on the fixed polarization. Okay? Curved semistable Higgs bundles are related to positivity conditions also by the following results given by Ugo and Bea in the first time, and in the second time also by myself. What do I mean? If E is a curved semistable Higgs bundle of X, and if the first check class is nef, then E is H-nef, Ugo and Bea. If the first chain class of E is ample, then E is Higgs ample. This is a result given by Ugo, Bea, and myself recently. Okay, now I skip this part. sorry. Now I start the last part. Okay, just a little bit of history. Let X be a minimal smooth projective surface of general type. Idest for the canonical bundle of these surfaces is nef and big. It is known that the chain classes of these surfaces satisfy the Bogomolov-Miyaoka inequality, which I report here. If the underlying field is the complex number fields and this inequality is saturated, then the cotangent bundle of X is ample, and 2 times the arithmetic genus of C minus 2 is greater or equal than 1/3 of the degree of the canonical bundle restricted to C, where C is any projective curve on X. This is a Miyaoka's result. This condition says that minimal smooth projective surfaces of general type, which cotangent bundle is ample, are algebraically hyperbolic. I record this later. In 1988, Simpson, ever over the complex number field, introduced the so-called Simpson sorry. I start again. In 1988, Simpson introduced the so-called Simpson system, which is a particular Higgs bundle given by the direct sum of the tangent bundle of X with the structure sheaf of X and by from this Higgs field. He proved that in the case of the minimal smooth surfaces of general type, which Bogomolov-Miyaoka is equal to 0, he proved the stability of this Higgs bundle. Okay, this is the history. Now, what's new? If consider a smooth projected surface over K, not over C, over K, where the canonical bundle is big and nef, me, Ugo, and Bea, we proved that if the Bogomolov-Miyaoka is saturated, we proved first the Simpson system is curve semistable. The canonical bundle is ample. Any projective curve satisfies this inequality. It has the surface is algebraically hyperbolic. The Simpson system is ample, and in particular, the cotangent bundle is ample. Sorry. Okay, this result is based on this lemma, which I proved in my PhD thesis, where I assume the ampleness of K, the canonical bundle, implies that the Simpson system is semistable with respect to K of X, Kx. Just 2 simple remarks. The Simpson system, the vector bundle underlying the Simpson system, is neither ample nor semistable. The Simpson system is ample and semistable only as Higgs bundle and not as ordinary vector bundle. And there exist smooth complex projective surfaces Z with ample cotangent bundle such that the Bogomolov-Miyaoka inequality is not saturated. So this condition is fundamental, otherwise these theorems do not work. Okay. This is the situation for the surfaces. In general, in higher dimension, ever in my PhD thesis, I have proved that the Simpson system is again semistable with respect to the canonical bundle. And I have found another proof of the Guggenheimer-Yau inequality, which is very, very known in differential geometry. I have found another proof which works over every algebraically closed field of characteristic 0, and that's it. What's the new part is the following. This is a work in progress, sorry. If the Guggenheimer-Yau inequality is saturated, then again the Simpson system is curve semistable. The discriminant class by previous results vanishes. by previous results, S is semi-stable with respect to any polarization of X. The Simpson system is example, hence again the cotangent bundle is ample, and this is a classical result. And any projective curve C on X satisfies the inequality 2 times the arithmetic genus of G minus 2 is greater or equal to 1 over n plus 1 times the intersection degree of K with the curve C. It has X is algebraically hyperbolic. Okay. To be clear, it is known that any smooth complex projective variety whose canonical bundle Kx is ample are algebraically hyperbolic. This is known. What was unknown in the best of my knowledge is the following value. I mean, this one.
Excuse
For
me,
what I
Armando.
know,
What do
yes?
you mean by algebraically hyperbolic?
I mean, that's the point. Variety is algebraically hyperbolic if any projective curve C on X satisfies this inequality where instead of 1 over n plus 1, one path a real positive number epsilon. Okay? Do I need to repeat?
Okay, no, thank you. Perfect.
Okay, this is a definition. Smooth projective variety is algebraically hyperbolic if there exists a positive real number epsilon such that 2 times PA of C minus 2 is greater or equal to epsilon
Okay.
degree of K restricted to C. This is the general definition. This is a very classical definition given by, if I'm not wrong, by Kobayashi
Okay.
or Demeyi. I don't remember. And we know that there exists epsilon a blah blah blah, a lot of properties, a lot of open conjectures, so very very interesting word. But I repeat, from what I know in my the best of my knowledge, there exists epsilon positive blah blah blah. Stop. This from my studies, from my proofs, it results that in this case epsilon is greater or equal to 1 over n plus 1. And this results agrees with the original Miyaoka's results for surfaces. Okay? This is very new. For me, I don't know what are the possible consequences of these bounds for this real positive constant epsilon. On the other hand, this bounds is not sharp. Indeed, if one consider the fake projective planes, applying these inequalities, one proves that all curves in the fake projective planes have genus at least 2. But by results of Di Cerbo and Keum, we know that this curve has genus at least 3. So this inequality is not sharp in general. Okay, how this property is related to positivity conditions for Higgs bundle? Now, I give just a sketch of the proof of this fact. Okay, first part, we know, okay, first step, I consider the Simpson system. By meta-Ramanathan theorem, I can restrict my Simpson system to a generic curve in the linear system given by the canonical bundle, which is ample by hypothesis. I studied the quotient Higgs bundle of this Simpson system. I proved that the slope of the Simpson system is greater of the slope of the Higgs quotient bundle of it. So this is semi-stable over the generic curve. It is semi-stable. This is in general. Stop. Second step, if I assume that the Guggenheim-Yau inequality is saturated, then it is also curve semi-stable. This is the first step, and this concludes the first step. Okay, second step. I twist the Simpson system by minus beta k of x, where beta is a rational number less or equal than 1 over n minus 1. Since S is curve semi-stable, then the minimum slope of f back of s beta is equal to slope of f star of s beta. And by simple computation, this is equal to the following number. And of course, by simple computation, one has this inequality, because I repeat, the canonical bundle is ample. Here, f is amorphous from C to X. By the Higgs nefness criterion, sigma S beta is Hnef, hence omega beta is nef in the usual sense. Now, I consider the normalization tilde C of C. I consider the pullback of omega 1 over n plus 1. A quotient line bundle of this vector bundle is the following. This is a twisting of the canonical bundle of the normalization of C. By the previous step, iota pullback of omega 1 over n plus 1 is nef. Hence, this quotient line bundle is nef again. Hence, we obtain this inequality, which is exactly the algebraically hyperbolic condition for X. After this, if I put beta equal to 0, I obtain from the ampleness of Kx the Higgs ampleness of S, hence one find again the usual ampleness of the cotangent bundle of X. And this completed the sketch of the proof. So, thank you so much for your attention, and I'm here in order to answer your questions.
Okay, thank you, Armando, for your talk.
Thank you.
Let me just check if there is any question in the chat. I don't see questions, but I have a question. I confess, I was all the talk thinking on the following. What if you want to extend this to Higgs bundles with logarithmic poles along a divisor? So if it would be possible to think on you fix a divisor on your smooth surface, think on surface, not I mean just dimension 2. Then you will have a divisor, just a curve, and it will, I mean, and then maybe it is possible to understand this curve stability, but this curve stability will be having some intersections with the divisor. So that will be like a parabolic stability or a logarithmic stability over the curve. You know, so I mean, when you have mark points over the curve, then you think on Higgs bundles with logarithmic poles over that point. So have you ever thought on that thing, or do you think that it will be possible to understand that?
Okay, I understand your question, but I never tried to study parabolic structures on Higgs bundles, so I don't know.
But without parabolic structure, just the pole, just having, then you will have the definition will be, you will go to the canonical bundle or to the cotangent bundle times this structure sheaf of the divisor. That will be the definition of your Higgs sheaf, or your Higgs field over your Higgs, for your Higgs sheaf.
Surely, in general, I think in general the answer is no, because we need to put opportune order of poles over these curves, I guess.
Okay.
Because in some sense we need to preserve the positivity conditions of the Higgs bundles. This is my idea. Of course, we need to take a paper and pen to compute
and check it.
everything.
Yeah, I see. But that's your I mean, that's your intuition. Thank you. Okay, that's good. Thank you. It's helpful. Thank you. Also, just a very curious question. I don't know, but in your examples and also in Simpson example, you always think on nilpotent Higgs bundles. Is this for any reason, just because of it's easy for computations, or is there any deeper reason?
Both. First, the nilpotent Higgs bundle or OJ Higgs bundle are easy to compute the relevant Higgs-Grassmann scheme.
Okay.
It's easy, not
Well,
easy between quotes.
okay.
In general, if I'm not wrong, Ugo Bruzzo and Daniel Hernández Ruipérez, they computed all Higgs-Grassmann schemes of nilpotent Higgs bundles, which are that sum of line bundles.
Okay.
And I don't remember the year, maybe 2005.
Okay, long ago. Okay.
In that example, they found for too much line bundles, one finds reduced components,
Okay, I
just
see.
over curves. So yes, easy. Then the general case, I repeat, if you take rank 2 vector X bundles with any conditions over the X field, the situation explodes.
I see. I see. Okay, it's worth it to check.
And maybe you can find also example of X bundles which has no quotient bundle,
I see. Okay.
just over curves, for example.
Okay, I see. I see. I see. Thank you. Well, okay, nobody got him, well, brave enough to make more questions, but so let's thank Armando again. Thank you very
Thank
much
you.
for your talk, and thank you for giving us your time and a
No, thank
splendid
you for the
talk.
invitation.
Okay, let me stop the screening.